Hello and welcome to chapters 8A through 8D, Time Value of Money, helpful information for the entire suite of time value chapters. So the first thing I'd like to go over with you is our set of key time value formulas and when we should use each one. So in chapters 8A through 8D, we encountered really only three classes of problems in terms of organization of cash flows. The first one that we encountered in chapter 8A was the set of two cash flow problems, sometimes called lump sum problems. These are characterized by having only one future cash flow, and the cash flow diagram for these guys looks something like this. We might, for example, invest in a project, negative cash flow for us at t equals 0, and then get a bigger pile of money back at some time in the future. So that would be something like a zero coupon treasury bond or et cetera, et cetera. So we had two flavors of formula for this type of problem. The first one was FV equal PV times 1 plus R to the T. And we noted that oftentimes in finance, we really want to focus on the cash flows of a project. So we could rewrite this as our cash flow at future time, T future, is equal to the cash flow at time 0 times 1 plus R to the T, where again, we're using common sense to worry about the signs of the cash flows and things like that. Next up, we looked at situations with multiple future cash flows, the general case of that. So this is a case where, as you can see in this free body diagram, we have more than one cash flow occurring in the future. And in general, the future cash flows might not be of the same magnitude, and they also might not occur at uniform time intervals. They happen to, in this cash flow diagram, happen at uniform time intervals, but there's no need for that. And we looked at some examples where they didn't. So this would be a typical cash flow diagram for the general case of multiple future cash flows in a problem. So there was really just one formula that we used to help tackle this type of problem, and that was to say that PV total, which is the cash at the beginning of the project, the cash we might invest in the project, so we call that PV total or cash flow 0, is equal to the sum of the individually discounted future cash flows. So the CF0 is going to be the 6K discounted back to t equals 0. So discount it back first, then the 8K discounted back to t equals 0. Then you add them up. That's the way that summation sign works. And this was called the fundamental discounted cash flow equation. The third type of cash flow scenario that we looked at was multiple uniform future cash flow situation, is where we have future cash flows that are uniform in magnitude and timing, and these were introduced in CH08b, and a typical free body diagram for this type of thing would look like this, where we have our PV total or our CF0 down here. Let's write that in. And then all of the future cash flows are the same magnitude, and they happen at the same constant interval in time. So we had several formulas to deal with this type of problem. The first one was our general formula, which was actually just a simplified version of our fundamental discounted cash flow equation. This looks just like our fundamental discounted cash flow equation, except because all the cash flows are uniform and occur at uniform times, we could pull them out of the summation. So you see here in the general case, because they're not all constant, we have to keep that term in the summation, but out here they're all uniform, so we can pull it out. So we could make that slight simplification. We also had a couple of other very helpful formulas for this type of problem. So here is helpful formula A, and this is helpful to quickly solve for us PV total or CF0, or on the other hand, our uniform cash flow, which in this equation is called C but as we all know, this C is equal to what more often we call CF, short for constant cash flow. And key thing to remember about this one is that it does not work for annuities due. You don't want to forget that. But that leads us right into helpful formula B. This is for annuities due only, and it's helpful in exactly the same way that helpful formula A is. We want to use it to help us quickly solve for our uniform cash flow or our CF0 or our PV tote. And the key thing to remember about annuities due is that the cash flows occur at the beginning of the period, not at the end of the period. And really, our only example use case for these was leases. Okay, so that's it for the types of cash flow problems that we looked at and the associated formulas that we needed to use to help solve all those types of cash flow problems. Next up, I want to talk a little bit about APR, NativeR, and EAIR rules, and this all came up in Chapter 8C. Here are some good rules that'll always lead you to the right answer for problems where you have an APR to worry about or an EAIR to worry about. So thing number one is we always want to convert APRs to NativeRs before using any of our time value equations, because the APR, as we know, is really a useless quantity, so it doesn't work in any of our time value equations. So why do we torture ourselves with APRs if I'm telling you they're useless? Again, because they are used, usually for nefarious reasons, by many banks, etc., in their advertising. They also come up in some of our bond examples. Okay, so second thing is whenever possible, once we get rid of that APR, once we've squashed it like a bug, we want to solve our problems in our native units for R and the corresponding time units. So for example, we get our R into 6% compounded quarterly, and then we're going to measure T in quarters, not in years or days or months or something like that. And then third rule is use EAIR only when you need it to solve a problem. So I might give you an EAIR and ask you to find the R. I might give you an APR and ask you to find the EAIR. So in that case, you'll have to go from APR to R to EAIR, that sort of thing. So if you follow these three rules, you should always get the right answer for problems involving APR and EAIR. And if you're interested in knowing why, I know that at least all one of you out of 450 are interested in why, hopefully more. You can read all about it down here, and I explain why these rules need to be applied to ensure you always get the right answer. And that's it. I'll look forward to catching up with you in the next video.